Um, as Ali previously introduced, my research experience mainly lie on the text-to-video generation. For example, the LVDM and Video Crafter, which is the early open source text-to-video diffusion models, and also Scale Crafter, which is IKEA's light paper for enlarge the generated resolution for image and video generation, and also the controllable video generation, like adding a story for your post and for your clips for the character control, human host control, and the local region control. And also for multimodal generation, like seeing and hearing, which is the versatile framework for both image, video, and audio generation. Okay, today's topic is it's about large language models with image and video generation. So let's firstly have a general overview of the background. In short, the achievements of large language models like GPT family and also image and video generation like Stable Diffusion, Flux, and Sora can be attributed to the large-scale generative pre-training. Like in the field of the ARP, the transformer architecture is a milestone work and demonstrate great capability in language tasks like machine translation and document generation. The advantage of transformer is its great scalability, and it can be trained with millions and billion level of model parameters. So it's adopted in most of the following large language models like BERT and GPT. And also the model parameters is continually increasing into 1.8 trillion parameters in ChatGPT. In the field of image generation, the generative models have changed from GANs to diffusion models. For example, in 2019, the most popular image generation model is StyleGAN and can generate the aligned human faces. But due to the minimax player GAN between the generator and discriminator, the training of the two models is very hard and unstable. So this makes GANs hard to scale up to a more diverse distributions, like the ImageNet distributions or the open domain image distributions. So the open domain image generation is achieved by diffusion models like Latin diffusion models, imaging, DALI 2, and also autoregressive models like DALI. Recently, image generation fields start to involve large language models to build a more interactive and free-form image generation system, which can generate image within a dialogue. And also, users can perform interactive image editing through the dialogue with the robot. Like, firstly, ask the GPT to generate an image about the dog, and after that, make the generated dog to further wear sunglasses. The model parameters of text-to-image models are increasing as well. For example, the Stable Diffusion initially has only around 1 billion parameters with UNet-based architectures, and the Stable Diffusion 3 has 8 billion parameters, and the recent proposed Flux has 12 billion parameters. And both SD3 and Flux adopt the Transformers architecture. In the field of video generation, the generative models also have the change from video GANs to video diffusion models. We can see that in 2022, the StyleGAN performed well on the Sky video generation, but it failed to generate human actions in UCF 101 dataset, which is a little bit diverse video content. But with video diffusion models, we can generate various contents based on the text input. So after VDM, the text-to-video generation had a great development and achieved surprising performance. We can see image and video from Google and Sora from OpenAI. Also, the model parameters of text-to-video models is increasing. For example, the Video Crafter tool has 1.8 billion parameters with 3D UNet and transformer modules. And the Open Sora, which is a recent open source text-to-video, Sora-like text-to-video models, which has 5.8 billion parameters, and also the top video, which has better performance recently has 5 billion parameters. So we can conclude that the large-scale pre-training demonstrates significant performance in both language, image, and video generation. Based on this background, we have a question. Can large language models help the generation of images and videos? The answer is yes, and we conduct comprehensive reviews and has the conclusion that the large language models have the generation of image and video in various aspects. Given the basic pipeline of image generation, where we input a text and to a text-to-image model, we can use large language models to provide a better conditional embedding. And also we can break down the text-to-image process into multiple steps generation and use large language models to planning the spatial layouts and the quantity values. And also after the image was generated, we can use large language models as an evaluator to measure the generated quality of the content. And also we can use large language models as a unified backbone for different modalities. And to prepare a better data set, we can use large language models as a captioner to provide detailed image and video content descriptions. Also, we can use large language models as multiple agents and learn to invoke different tools. For example, text-to-video models, text-to-image models, and like image and understanding models, etc. So then I will introduce these aspects in detail. First, large language models as a unified backbone. Here's an example from VideoPoint. So if we can project the data of different multiple modalities into unified discrete tokens, just like the text tokens in large language models, and then we can directly adopt the architecture from the large language models and perform the next token prediction task. So we have text input to the T5 encoder, and we get the text tokens. And also we have the image depth optical flow and videos and input to the MACVIT V2 encoder, and we can get the visual tokens. Also, we have audio, and we input the audio to the sound stream encoder and got the discrete audio tokens. And then we can perform the next token prediction task in a unified manner. For example, we can fuse the different modality tokens and construct the input sequence and also the output sequence. And we make the large language models to predict the output tokens autoregressively. After we get the output tokens, and we can decode these tokens using modality-specific decoders. So this unified training paradigms can achieve the various tasks, including text-to-video generation with audio, and also video painting. Here's another example for large language models with the image modality. So here's a common goal that to make the large language models have the ability to understand and generate information of other modalities. If we achieve this, we can use the unified system to achieve the image captioning or ask the large language model to generate images, or we can perform the interactive multi-run image editing following the human instructions. Also, we can generate and edit different modalities such as image, video, 3D, and audio. Here's also the multimodal autoregression with visual tokenizers. So we have vision tokens and text tokens, and also vision tokens. We can perform the next token prediction to integrate the image information into the large language model usually the large language models, it's a pre-trained one, which is different from the previous video point, which is trained from scratch. And also, this is the details of visual tokenizers and detokenizers. So firstly, to encode the image into the pre-trained large language models, we firstly need to train image tokenizers and detokenizers. This is multiple training stages. So firstly, given an input image, the seed firstly train a causal Q former, which projects the image feature from that encoder to a causal embeddings. And the causal Q former is trained via a contrastive loss. And after that, they train a visual codebook to discretize the causal embeddings to discrete codes. And the training loss is to maximize the causal embedding cosine similarity of the causal embeddings. So the causal embeddings is learned via a causal manner during training. In detail, the query embeddings can interact with only previous queries through self-attention layers with a causal mask. And after the image tokenizer and detokenizer is trained, then they inject the image tokens into the large language models and perform a multi-model auto-regression training. So giving image text pair data set, they construct the auto-regression training like they formulate the task with image to text auto-regression text. So the first previous tokens are image tokens, and then the output tokens is the text tokens. Also, the text to image generation task, which is the input tokens, is the text tokens, and output tokens are image tokens. So they fine-tune the large language models with LoRa and train with 5 million image text pairs in CC3M, Splash, and Coco, such image caption dataset. And the second aspect is utilizing large language models as planner. So the basic idea behind this is we can always instruct the visual generation model in detail. So for example, a common process for generate image is input a prompt, and we have one model which condition on the text embedding, and we can output the image. But with large language models, we can firstly utilize it to generate the spatial layout, for example, bounding boxes of different objects. And then we utilize a bounding box conditioned text to image model to generate the final image. So this can help the quantity correctness of the text to image task. For example, the input prompt is there are 3 elephants standing beside a pool of water. If we utilize a common text to image model, it can only generate 2 elephants. And if we firstly generate the layout, which can constrain the object with a bounding box, and then after that, we generate the final image. The quantity will be aligned with the input prompt. Also, another aspect is the spatial position relation. For example, a carrot and some onion next to a knife on the cutting board. If we directly input the complex prompt to text-to-image model, it's hard to get the correct spatial position relation. But if we firstly generate the layout and with the specific objects, and then we generate the final image, the spatial position will be aligned well with the input prompt. So how to how to make large language models generate such layouts. We can utilize simple prompt engineering, and we tell large language models the task is to generate the layout of the image, and the generated layout should follow the specific CSS style. And we also provide the large language models with some in-text learning examples, like we have a prompt and layout data, and we provide such examples to large language models, and then we can provide a new prompt, and large language models can generate the new layout for the given prompt. And after that, we can use the layout to image models such as Yingqing to achieve the final image generation. Also, it can help the video generation regarding the multi-scene long video generation. So here we can first conduct the prompt decomposition for the long video generation. For example, we want a young man with blue hair is making cake, and we tell the large language models you need to envision a multi-scene video, and then they will give the descriptions of different scenes. So first, the large language models will decompose the detailed steps for making a cake into multiple steps, and we get the multi-scene video scripts, and then we can based on the different scripts to generate the different scene clips. And for each scene descriptions, we can get the multi-view and multiple actions to generate the long video clips. And also, we can make the large language models to describe the entities in the long videos in detail. For example, the large language models can act as a director to firstly describe the young man and cake, the kitchen, and the dining room. And we can fed these entity descriptions into a text-to-image model, and we can get this appearance image. And we need to make these entity images be consistent across different clips. So in order to achieve this, we can train a foreground and background condition text-to-image model to conditions on the entity's appearance image, and then we can get the different scene image to represent the appearance of different video clips. And after we get the scene image, and we can leverage an image to video model to generate the movement of different clips. So to train the foreground and background control text-to-image model, we can leverage a pre-trained text-to-image model and add to extra condition modules to it, and then we fine-tune the cross-attention modules of the two conditions to get the final controllable text-to-image model. And here's another example of large language models as a planner in the task of generating high resolution image generation. So the basic pipeline for 23 high resolution image generation is that we want to make a pre-trained text-to-image models, which is trained in a lower resolution, and we hope it can generate a higher resolution than its training resolution. So the basic method for this task is we input a prompt to the low resolution model, and we get a low resolution image. And after that, we interpolate the image to a higher resolution, but the image will become kind of blurry. So in order to increase the texture details of this image, we will patchify the larger images into different patches, where the patch size is same with the low resolution text-to-image model. And then we add noise and we add noise to the different patches, and we fed the patches into the text to image models to generate some texture details. To generate the texture details of each patches. And after that, we fuse the different patches together to obtain the final larger image. But here's the problem that if we share same prompt across different scales, then the prompt will be misalignment with the actual content. So utilizing the large language models, we can generate the descriptions of multiple pages, and then we utilize the detailed and accurate patch descriptions to instruct the text to image models to generate some local image details. And another aspect is leverage large language models as captioner, which is performed very effective in the DALL-E 3 paper, which they find that training on long synthetic captions achieves the best performance with clip score, and it performs very well in both the ground truth captions and also the long synthetic captions. And another usage is to generate the detailed image descriptions to automatically get the caption dataset. So, for example, if we're using Coco to get the captions, the descriptions is relatively rough, and also the Lava is some multimodal large language models, and the shared GPT 4V, which is widely used in the image captioning and construct the large-scale image and video dataset. And here's an example from the speech audio generation. And firstly, we need to extract the descriptions of the speech style in order to achieve the text-to-speech generation with different speaker styles. So firstly, we have a human speech audio, and we use several attribute classifiers to get the attributes and tags of the attributes we want. And then we use Llama 2 to transfer the attributes and its values into natural human languages. So in this way, we can construct the human language with the human speech pairs to achieve the various styles text-to-speech generation. And another aspect is large language models as conditioner. So it's a kind of intuitive, and in this, here's an example from text to audio generation, which they leverage the Plan T5 as a text encoder to encode the input text prompts into text embeddings, and then they fine-tune the text to audio diffusion models to adapt to the new large language models embeddings to achieve a better semantic understanding for the generation model. And then is large language models as evaluator. So we can use large language models to evaluate the generated quality of our models. For example, giving a prompt, a little girl wearing a bright yellow dress and a corporal crying is riding a badger through a field of flowers. And we ask the large language models to generate a few questions of the detailed attributes of the prompt. For example, is there a girl? Is there a girl riding through a field of flowers? Is the girl wearing a crown? Such questions like that. And then we fed the questions into the VQA model and also input the generated image to the VQA models, and use the model to answer these attribute-specific questions, and we can get the result from the VQA models, which measures the actual semantics of the generated image. And then we can calculate the alignment score between the actual generated image with the desired semantics of the prompt to measure the attribute alignment of the generated image. And after we get the semantic alignment score of each generated image, we can filter the generated results and obtain a new subset of generated images with very high semantic alignment scores. And then we use this subset to directly fine-tune the text-to-image model. And after tuning, the text-to-image models has very better semantic alignment. We can see that the before tuning, the text-to-image model is hard to understand the complex semantics, but after tuning with high-quality generated examples, the semantic alignment be significantly improved. And also, large models can serve as multimodal agents, which is very helpful to dealing with complex tasks or using instructions. So the complex task can be the complex task is like the complex content, for example, a very long prompt with multiple objects and attribute binding, position relationship, and object quantity. And also, we may need a multiple task or multimodal system. For example, can you generate a video of a car running on the road? Is a task of video generation. And then can you generate the corresponding sound? Is a video to audio generation. And then user asks, can you modify the car into a big blue truck? Is a video editing task. So the large language models can has the potential to unify the multiple tasks in one system. And a basic pipeline for large language models as agents is like, firstly, we have user instructions, which may be a multiple model task. Like, can you dub the video with subtitle background music, and then generate a web page to introduce the video. And given this complex task to the agent, the large language models can firstly decompose the task into several subtasks. For example, the first subtask is to matching the video with the background music. So this is a video to music task, and the second task is generate a web page to introduce the video. So it's a HTML generation task. So after the task decomposition, the large language models can planning the task into a tree structure, and it can search for finding optimal task tree to get the workflow of the different tasks. And after the task planning, the large language models can invoke different tools within existing toolbox. And the toolbox may have different models or different experts. And also the large language models can execute the different tools based on the planned tasks. And after that, the large language models also can summarize the output and to formulate it into a desired output with multiple modalities and return it to the user. And another example is for the text-to-image generation and editing. Like we give a complex prompt, and we can firstly decompose the input prompts into different objects, and then we do the task planning and output a task tree, and And then we can following verification steps, and we check whether the objects and the spatial layout and background and style is correct. And then we can conduct the position aware to execution to generate the image, and then we can do the self correction for the output image to get a better results. And the toolbox here involves multiple models, including the text to image model, image to image model, layout to image model, and also super resolution, object detector, object segmentator, post estimator, layout generator, and some editing tool library like object addition, object removal, etc. So to conclude, the large language models can help visual generation in various aspects, including the unified backbone, planner, captioner, conditioner, and evaluator. So I think the next possible direction is to how to leverage the powerful large language models to improve the visual generation performance, also how to improve the learning efficiency during the large-scale pre-training. And we can also think about more diverse methods and explorations from the different aspects. And also we can integrate the visual generation models into large language models to build a flexible and multimodal large language model systems. And we have released a survey paper, which is involved more modalities, including the image, video, and 3D, and also the audio modalities, including the sound, music, and speech. And we provide a more detailed review according to the different modalities, and you can check it more in our GitHub repo and our survey paper. Thank you. That's all about my sharing. And we have a few questions. I have one question. Based on LLMs, how do you see video generation can be controlled? Based on LLM, yeah. How to control the video generation process? Yeah, I think it has multiple level of controls. So we can use large language models to generate the prompt descriptions to decompose the text. Like we can tell the model how to perform an action like making a cake, and this prompt level control. And also we can use large language models to generate the video and temporal layouts like the bounding box sequences, and then we condition on this bounding box to generate the video. Yeah, and also we can like we can leverage other intermediate representations like the depth, also 3D scene layout, and also human poses to achieve the complex human action generation. Yeah, we will go to the coffee break.